Hello everyone. It is 6 p.m. I will wait for a couple of minutes and let people join. Otherwise, I will start the session after a few minutes. I'll wait for some more time so that people can join. And in the last few sessions, a few people have joined, so that's why I'm waiting. Otherwise, I will start the session and upload the recording. Okay, it's already 6:05. I will start the session now. People can join in between also. Hello everyone. Welcome to the live session for the course Sensors and Actuators. I am Ananya. So I will be your TA for the session, and this is week 5. So let me give a brief introduction about myself. So I'm a PhD student in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI, and I am conducting this live session as a part of my PMRFTA duty. Okay, so I conduct the session on every Tuesday from 6 to 8 for the course Sensors and Actuators, and I normally start the session with a brief introduction about the topics those were covered in this week, like for the respective week, and then I move to the problems or the questions. So the main motive for this live sessions are to solve problems. So these are basically tutorial sessions where I will give some problem and I expect that people will answer. So even though like right now, so normally what I do, I give the problem and then uh, wait for some time so that people can answer me in the chat box. So till now there is no student in this session, but I'll still take a pause, and then I will tell the answer even if no one will join the meeting, so that if you are watching in YouTube and the recording of the session, then also you can think and you can answer like for yourself. Okay, so there is one person who has joined. I hope I am audible to you. So I just gave my introduction and I will start the session. Okay, if you are new to the session, if you have joined the live session for the first time, then I'm Ananya. I will be your TA for the session. Okay. Do you have any question? You can unmute and speak. Anna, we have raised a hand, so if you have any question, you can unmute and speak, or you can write in the chat box also. I hope that I am audible and uh, you can hear my voice. Okay. Okay, I will start the session. If you have any question, please feel free to ask in between also. So this is week 5. I will start with a brief introduction about the topics those were covered in this week. So there are few lab classes also, and few console simulations were demonstrated. So I'll not describe those because the main motive for this live session is to solve problems. Okay. Thank you. Okay. So the first topic that was discussed in this week is about silicon and silicon as a substrate. So in this course we are mostly talking about different sensors which are like MEMS based sensor, and in many of these silicon substrate is used. We already know like how to pattern silicon very easily, like what are the material that can be used for etching of silicon or silicon dioxide. So all these things are already well known. Also like bulk micromachining and surface micromachining techniques on silicon substrate is also well known. The processes have been developed, so it is easy to work with silicon substrate, and that is why we are mostly focusing on silicon. But for some specific applications, there may be requirement of other substrates as well. Suppose you know the silicon is not transparent. If you want to use a transparent substrate, then glass can be an option. And if you want, say, some flexible substrate, then PDMS or any other flexible substrate can be an option. That depends on the application and the type of the sensor that you are designing. So we will talk about silicon here. Now you know that there are different types of silicon substrates available for us. So these are 111 p-type silicon, 111 n-type silicon, 100 p-type silicon, and 100 n-type silicon. Now this n-type and p-type depends, it is the doping of the silicon substrate. So this doping is not, this is like a very lightly doped silicon wafer. If we want to make certain reason of different like doping concentration, then we can dope it additionally later, but it has some like a background doping. So based on that, the substrates can be classified as n-type and p-type. Now based on the top surface, the plane of the surface, the substrates can be classified as 100 and 111, these two type. So we have overall 4 combination: 100 n type, 100 p type, 111 n type, and 111 p type. Okay, now you can see that this is the primary flat for this 111 p type, and there is no secondary flat for 111 p type. But in case of 111 n type, you can see this is the primary flat and this is the secondary flat. So primary flat is actually little bit longer compared to the secondary flat, and based on the placement of this primary and secondary flat, we can determine which type of wafer it is just by looking at it. Okay, so for 111 n type, the angle between these two, so these two flats is 45 degree, and in case of 100 p type, so this is 90 degree. You can see this is the primary flat and this is the secondary flat. And for 100 n type, so this is the primary flat and this is the secondary flat, so the angle is 180 degree. Okay, now this primary flat is along 110 direction, and the placement of secondary flat depends upon the type and the doping of the respective wafer. Now how silicon wafers are made, so this was discussed, I have already discussed in one of the previous week's content. I already discussed about this figure, like how silicon is silicon wafers are fabricated in a like fab. So this was discussed, so we already discussed this. I'll not go into the details. So just briefly that we'll start with a very pure silicon melt. This is the silicon melt. It will be heated, in this crucible. So this crucible has to be of certain material so that it can heat up to that high temperature. You can look any literature for that, what is the crucible material and what type of heater is used here. And then a seed crystal is dipped into the melt, and then the seed crystal is pulled upwards. So you can see here the crucible is rotated here in this direction, so this is counterclockwise direction, and the seed crystal along with the wafer, so this is the wafer. Okay, this whole ignot will be sliced into wafers later. Okay, so this is pulled in the clockwise direction, so these are two directions are opposite, and basically that's how this ignot is made. Now one advantage of silicon is that we can grow various sizes of wafer from this technique, like from this kind of a melt, and this is known as melt grown technique. And for any material for which we can make wafers from a melt grown technique is very useful, because we can produce it, we can go for production at a large scale. So that is always a advantage, when you can make a large batch of wafers in one go. Okay, so this is the process of how silicon wafers are made. Okay, now this is the crystal structure of silicon. So you know that this 111, 100, these are Miller indices. I hope that you already know what Miller indices are and what is 100 plane and what is a 111 plane. Okay, Okay, so if you look at the crystal structure of silicon, what is the crystal structure of silicon? You know that there are different types of crystal structures. So silicon is a FCC lattice, face centered lattice, but there is another face centered lattice which is interpenetrated, and it is shifted 1/4 of the diagonal. Okay, so this kind of structure is known as diamond structure. So silicon has this kind of, and because silicon is a crystal, so this has this kind of arrangement, atomic arrangement inside a silicon bulk material. Okay, now you can do all kinds of calculation. So if we have a cubic kind of lattice, cubic kind of crystal, you know what is 100 plane. So if this is your cube, so if you consider this as your origin, so you can consider any point as your origin. Okay, I'm considering this, and this is say x-axis, and this is y, and this is z. Now why you can take any point as origin, because in crystal ideally, so this is periodic, this structure is periodic in all three dimensions. So basically if you take this cube or the cube adjacent to it, it will look similar. Okay, you can just take one point and do your calculation. So if this is your origin, then this plane, I'll use a different color maybe. Okay, so this plane is your 100 plane. I hope that you already know how to get these Miller indices. Now next, if it is say we have the same crystal structure, we have this cubic structure, and this we are considering the same point as our origin. This is x-axis, this is y, and this is z. Then our 111 plane will be, okay, so that my diagram is not very clear, but you can see that this is our 111 plane. This plane cuts the x-axis at 100, y-axis at 010, and z-axis at 001. So that is why this is 111 plane. Okay, now if you look at the silicon crystal structure, so this is 100 plane, and 111 plane will be this, and you can see that the atomic density in these planes are different. Okay, and that is why if you have a 100 silicon wafer, it will be less reactive to, like say, some surface phenomenon. It will be some less responsive in a surface phenomenon compared to 111 silicon, where because of the more atomic density for surface reaction, the reactivity will be more. So based on that, you can determine what kind of silicon wafer you want to use for your application. If there is if it involves some surface phenomenon and you want this surface activity to happen, then you'll probably go for 111 silicon wafer. And in mostly in CMOS devices, 100 silicon wafer is preferred. Okay, is there any question? I'll take a pause here. Let me see how many people are there here. Okay. Next, in the lecture videos, what was discussed about silicon dioxide. Okay, because we are discussing about silicon as a substrate, then this is the dielectric that we often talk about, silicon dioxide. Now, this is a figure that I have taken. This was given in the lecture video also. I have taken this from the book, this book, Silicon VLSI Technology Fundamentals, Practice and Modeling. So this is a very nice book if you want to know about silicon, like fabrication of silicon wafer, different fabrication processes and technologies those are used like for CMOS fabrication or any silicon based fabrication. So if you are interested, then this is the book. So this is the front page. I had this hard copy and I have taken this figure from there. So here you can see that uh, use of silicon dioxide is given depending on the oxide thickness. Okay, if it is a very thin oxide, so you know that if you keep your silicon wafer outside, it will react with the oxygen molecules from the environment and there will be a very thin silicon dioxide layer on top of it, even if you start with a pure silicon wafer. Okay, so this a small thickness, very thin silicon dioxide layer is maybe present on your silicon wafer, and even if you so this very thin layer, which will be like 1 to 2 nanometer, this is known as the native oxide. So so this very thin layer is known that. Now if the thickness is between 1 nanometer to 10 nanometer, so this is gate oxide or tunneling oxide. So gate oxide is the, like, you know what is gate. So it is the third terminal in a MOSFET device. Okay, so you know how a MOS structure is, what is the structure of a MOSFET. So we have a gate, we'll have a dielectric layer in between, and then we have the bulk material where the channel will be formed, right? So that gate oxide is often SiO2, because we can very easily grow SiO2 on silicon. So the thickness is very small, and you know that with device scaling this thickness is getting lower and lower. Okay, and nowadays we use different oxides rather than silicon dioxide, but that's a different topic. But we can always use sorry for that, we can always use silicon dioxide as a gate oxide. Okay, now thicker than this, from say 10 nanometer to 0.1 nanometer, 0.1 micrometer. So this can be a paired oxide or a masking oxide. So what is a paired oxide and what is a masking oxide? So masking is like, say you are doing bulk micro machining of silicon. So this is your silicon, and you have patterned your SiO2 like this, and you are using as a mask here. Now you can do micro machining here, or you can go for, like, if you have a silicon wafer and then you have made a opening like this using SiO2, then you can go for doping here. Okay, basically it is used as a mask, like a covering for the silicon below it. Okay, so we often use silicon dioxide for this purpose, and paired oxide is that because we know silicon dioxide is amorphous in nature. So many times, instead of putting like strain and stress from any other processes, we use an SiO2 layer as a paired oxide, so that no stress and strain is created because of any kind of harsh treatment. Okay, and if it is a very thick, then it is a filled oxide. You must have studied about, if you are from electronics and communication background, then filled oxide maybe you have studied in any CMOS courses. Okay, so you can see that SiO2 has many application, and in this course we have already discussed like how we can use SiO2 as a kind of like a masking layer. So, when say you want to make a heater and an interdigitated electrode on top of it, then in between, because heater will also have some metal lines and interdigitated electrode will also have metal lines, to separate out these two layers we use a SiO2 layer in between. Okay, this is like a separation or masking layer, you can say. So silicon dioxide is like very well known. Silicon and silicon dioxide interface is very well known. We can grow silicon dioxide very easily in on silicon, and that is why what is the most important advantage for us, because we know how what is the interface looks like and how we can grow silicon dioxide, and the properties of silicon dioxide is such that we can use it for different purposes depending on the thickness and the purity of the layer. Okay, so for to make a gate oxide we need a very good quality of SiO2, and suppose we are just using it as a filled oxide or as just as a separation layer, then we can go for a little bit of low quality SiO2 with some defects, say, but those we can grow, will grow a very thick layer. So that we can grow it easily, we will use some technique that will give us a higher growth rate. Okay, now I will write down few properties, like not properties, why we use SiO2 so frequently, and why in along with silicon. So I'll write down few. Okay, first is it's a very good electrical insulator. Okay, so if you want to make if you separate if you separate out two layers, electrically insulate two layers, then it's a very good choice. Now what property actually defines that it's a very good insulator? So you can look for what is the resistivity value of SiO2. That will indicate that if it is highly resistive, then it is a very good electrical insulator, right? So you can compare the resistivity value of SiO2. You can find it in Google or any other book. So what is the value of resistivity for SiO2 and other maybe dielectric, or if you it can compare with different types of material. Okay, another property is its thermal and chemical stability. Now what is the temperature, uh, what is the melting point of SiO2, like at up to what temperature it will be stable, that you can check. um, it can easily sustain like 1000 degree Celsius, or maybe a little bit higher than that, I don't remember the exact number. So why it is important? So if you want to use it for certain fabrication processes where it will be required that, so you will use it, you will do the process, you will do the fabrication, or whatever the process required, that will be at a very high temperature. So that, so suppose a certain reaction has to happen, and that reaction happens at a very high temperature, so you definitely want a material that can sustain a very high temperature. So SiO2 is a very good choice in that matter. And chemical stability, we know that, see, certain chemicals will etch silicon. Say if we want to go for bulk micromachining, then KOH will be etched, it will be an etchant for silicon, but KOH will not damage SiO2. So all these things are already well known. That is why we use SiO2 so often as a good mask, if we want to use it along with silicon. Third is easy to grow and deposit. we know that there are like wet and dry oxidation techniques for growth of SiO2 on silicon. Okay, and we can deposit SiO2 on substrates also using certain techniques like PECVD, and it can be done using sputtering also. Like in our lab we have a SiO2 target, we use it for deposition of SiO2. So uh, all these things are already well known and it is easy to do. And another property of SiO2 is optically transparent. It is. So why it is important, as I mentioned that it is very stable. Like if you have a SiO2 layer, and it the degradation of the SiO2 layer will be like almost negligible. And suppose you have already made a material, so you have already made a device, and that is for some uh, say purpose where there will be something like color change or something that you have to see, like that has to be visible. So but the device itself degrades if you keep it in like say normal environment, okay, due to temperature, humidity and all other things. So what you can do, you can make an SiO2 layer, we can deposit a SiO2 layer on top of it, so that will act like a passivation layer, and it will be optically transparent. So it will not let the any damage or environmental degradation of the device, but you can still see the device through it. Okay, that can be useful in many applications. Okay, yeah, and this is the mechanical strength of SiO2 is very high. That's why we use it as a peroxide, and it can be used for MEMS devices. Okay, because if we are making a suspended kind of structure, we say sometimes we need a material that has a good mechanical stability. Okay, so these are the advantages of SiO2. I'll take a pause. If there is any question, I don't exactly remember how many of these were covered in the lecture videos. If I have missed something, then you can also let me know, like it can also remind me here. Okay. If there is no question, let's go to the next slide. Just give me a second. Okay, so the next topic is characterization techniques. So this was mainly discussed considering the thickness measurement of SiO2. Okay, so how we can measure the thickness of SiO2 or any other layer. So first technique that was discussed in the class was surface profilometer. So to use a surface profilometer, what we need to do, so this is like a destructive technique. So what we need to do, suppose you have the substrate and you have deposited or you did the like you have grown some thin film on top of it. So this is your film, and you will make a step here. Okay, and in what a surface profilometer will do, there will be like a tip. Okay, so and it will be scanned through the surface. So at this point it will see certain reference thickness. and then there will be a jump here, and there will be some other thickness. So the surface may not be very smooth, okay, even if the roughness is in nanometer scale. If you use very good system, there will be it will pick up some of the surface roughness information as well. Now from this result, what you will do, you can take this a reference here, and say average value of this reference, and this will be your thickness of the film. Okay, so now what we normally do is that how we do the measurement, we not only make like one step, we make multiple steps. So if I give you the top view of your film, so there will be multiple steps. Okay, like this. Now how you can make this kind of step, so your deposition, whatever deposition technique you are using, that will give you a uniform thickness, right? But you can put some tape or something like that to cover this area, and later on you can remove this tape to make this kind of a step. The good idea is to do a lithography to make the step. So there will be like a photoresist, and then you can remove the photoresist instead of a tape. So that will give like a very good interface, otherwise it will be very noisy data. So for like accurate thickness measurement, we go for photolithography to make this kind of a profile, and actually like multiple steps, so that you can measure your thickness reliably. Okay, one more advantage of making multiple step is that there may be some difference in thickness at one corner to the other corner. Okay, if you are not careful with your deposition techniques, then you will get to know about the thickness variation, say along this x direction or y direction also, if there is any variation in thickness variation in your sample. Okay, now this is about surface profilometer. The problem here is that we have to go for this kind of photolithography to make this kind of step, and so this is not an uniform film now. So this is like a destructive technique. So what can be other technique for thickness measurement? So thickness measurement can be also done from the reflection data. Okay, now for SiO2 we can just look at the color. Now for any other layer, it can be from reflection measurement. Okay, now how it is used, say suppose you have a substrate, this is your substrate and this is your film. So remember, this is a thin film compared to the substrate. The thickness of this film is very less. Okay, so this is say T naught. Now when light is incident here, so some light will be reflected. Okay, some will travel through the surface and then will be again reflected from this interface. So you know that when light incident on any surface, three things happen: it will be reflected, refracted, or absorbed, right? So we are considering the reflection data here. So some will be reflected from this top interface and some will be reflected from this bottom interface. Now this two wave, so this two reflected wave will have some path difference, because this wave is traveling some extra distance here. Okay, now because of this, if you know about how waves constructively or destructively interfere. Now the condition for constructive interference is that it will constructively interfere, and the equation is this: T naught is equal to k lambda by twice n, and k can be 1, 2, 3. This is the like the order. Okay, now this equation was given in the class, it was discussed also. So this is the condition to have constructive interference. And this condition is when the incident angle is 0 degree. So if I consider this is the incident angle theta, if it is 0 degree, then this is the condition for constructive interference. Okay, now you can directly use this equation to see what is to calculate what is the thickness of your thin film. Now practically how we will do, like so if you have reflection data of a thin film, so there will be like certain reflection maxima and certain reflection minima. Okay, so this is one reflection maxima and this is one reflection maxima, and this is say at lambda 1 and this is say at lambda 2. Okay, you can you can see what is this condition. Okay, so this lambda 1 and lambda 2, so suppose this is for k like say k1 and this is say k2, so k2 minus k1 is equal to 1. So this kind of calculations are not given, so I'm just giving you an example. Okay, practically what you will get, you will have this wavelength versus reflection data, and you will have some peaks where maxima is happening, that means constructive interference is happening, and based on that you can use this lambda 1 and lambda 2 value and calculate the thickness of the film. And how you can calculate, you can search in Google, you will find that. Okay, now for silicon dioxide, so the certain thickness, so one example was given in the class for different thickness of silicon dioxide, what is the color of the SiO2 layer, SiO2 film. Okay, so these are already well known because you see, so this is reflecting with a particular lambda 1. Okay, so if it is invisible, so there lambda 1 will be like it will mean some color. Okay, it will represent some color. Okay, so that's how the based on thickness, what will be the color of the SiO2 layer, that is already well known. So an expert user can like just look at the sample, and from the color of the SiO2 layer can determine that what is the expected thickness of the SiO2 layer. Now this is the expected thickness, and this can be done by an expert user. Okay, for like a normal user, we we will use like a instrument that will give us reflection data. We will use equations and we will put the values of like whatever data we are getting from the reflection, and then that's how we will calculate the thickness of our thin film or SiO2 layer. Okay, so let me go from, where's my cursor? The thickness of the SiO2 layer determines which wavelength lambda interference constructively. Leading to observed color. Now I hope that you got an idea how to do the how to measure the thickness. I know that I have not done a very good job explaining this. It would have been much easier if I have some reflection data and use like pen and paper to calculate the thickness. But this is just to give you an idea, and if you are interested, then you can look more about it. Now another technique that is used for thickness measurement, which is also non-destructive and that is more accurate rather than thickness measurement just by looking at the color. So the technique is ellipsometry. This technique was briefly discussed in the class, so if you are interested you can look more. The structure of the instrumentation is a bit complicated, and you know that it needs a little bit of concept about electromagnetic waves. You know what an electromagnetic wave is? It's basically light, right? It has two parts like phase and amplitude. So like you know what is the phase and amplitude of a wave, right? So it has so if a wave has this kind of phi, so this is amplitude and this is phase. So electromagnetic wave also have phase and amplitude. So based on that phase and amplitude information from the reflected wave, basically the thickness is determined. So there is certain calculation that is related. So this gives this instrumentation, this machine this measurement techniques gives us better result compared to other kind of techniques, because this is more accurate. Okay. Okay, is there any question? Did you like I know that you have already watched the lecture videos. If there is any doubt, like I tried to explain, but I know that I could not explain very precisely. Just give you a brief idea about how the thickness can be measured. Like many of your properties will be dependent on the thickness. Okay, so that is why thickness measurement is very important. So what we normally do in our labs after deposition, we always go for a thickness measurement, because that will decide a lot of the properties, and if we want to do make a device using those tungsten, so the properties will be dependent on the thickness. Okay, and suppose we want to scale up or down. Say we want to make the thickness twice, or like say we want to make the thickness half. So we should know the deposition rate, something called like. So suppose we are depositing for say 10 minutes. If we are doing the sputtering for 10 minutes, what is the thickness? If we are doing the process for say 20 minutes, what is the thickness? So what is the relation between the time, the position time, and the expected thickness? So that is what we try to measure, and after that it is easier. Say we want certain thickness, we can directly use that kind of equation, that okay, maybe if we do for this duration, we will get like the expected thickness will be this. Okay. Okay, next technique, it was briefly discussed. So the technique was uh, so one physical vapor deposition technique was discussed. So I have already discussed like what is the physical vapor deposition techniques. There are basically three types of physical vapor deposition techniques. First one is thermal evaporation and e-beam evaporation. You can just say like evaporation. You know what evaporation means? Like you evaporate the material from target and it will sit at the substrate. Now sputtering is little bit different. It is also a physical vapor deposition technique, where you will use a sputter gas to eject some material from the target, and that will sit on top of the your substrate. Okay, I've already discussed briefly about thermal evaporation and sputtering. In the class, thermal evaporation was discussed, so this is like a setup for thermal evaporation system. So you can see here, this is there is a pumping system. So we will first create vacuum inside this chamber where we will do thermal evaporation. Now why it is required? We don't want any particle, any contamination on our film or on our target. Okay, that is one reason why we go for a vacuum environment. And another reason is that so our target material will be here. Okay, so this is a board, okay, or a crucible. It can be of graphite, it can be of molybdenum board. Okay, this board will be of some material that can sustain a very high temperature, and we will keep our material, say aluminum or some other material here, and uh, this material will be evaporated, and this is our substrate where the film will be made. Okay, we don't want any scattering of these evaporated particles. That is why also we create a vacuum environment inside the chamber. Okay, if your vacuum is good, that means your pressure inside the chamber is very low, then your deposition will be better. Okay, you will get a very good quality film on top of your substrate. So I've already mentioned that why we need a crucible or a boat which can sustain a very high temperature, because as the name suggests, it is a thermal evaporation technique. We will apply electric current, a very high electric current between these two electrodes, and this will be heated up, and because of that, the material, target material, will be first, it will become a melt, and then it will be evaporated. Okay. So that is why to sustain that kind of temperature, we need a both material that can sustain very high temperature. Okay, now this is a substrate and this is a substrate holder. Okay, and many times we actually rotate the substrate holder so that there is uniform deposition throughout the substrate. Okay, this is an image of a thermal evaporator system I have taken from Google. You can see there may be different arrangement, there may be different kinds of boards. Sometimes we use a basket also. Okay, so this kind of a basket. Okay, this drawing is really bad. Instead of a board, so that is actually less costly. Okay, we will keep our material here, and we'll apply like a very high current at these two electrodes. Okay, so there what I mean, what I want to say that instead of one target, maybe we will have multiple targets in one system. So this is just a representation. The actual thermal evaporation system or machine can have different configuration, but the mechanism is same. We create vacuum, we melt our target material, and we keep our substrate holder normally at the top, and our target material will evaporate it, and with minimum collision it will sit at the substrate. Okay, so this is about thermal evaporation. And next, in this week, some COMSOL simulations were given. I will not discuss about it because I cannot show you, I cannot run the software in the live session, and I don't know whether you have in your institute whether you have access for COMSOL or not. So but you have already gone through the videos in NPTEL, so how we can use different physics, and how we can generate a structure using geometry, and what are the work sequence you have already learned when you want to use COMSOL for your to make your sensor design or for any other purposes. Okay, one example can be, say, if you are working on certain sensor that needs a heater, So if you want to design that heater part, say your material, your sensor will work at a high temperature, says at 150 degrees Celsius. So you need a heater design that can at least go up to uh, 150 or more. Okay, so you can do a simulation of your heater and see whether it can go up to 150 degree or a little bit higher than that or not. Okay, so basically before going for fabrication, you can simulate your design and optimize your design using this kind of softwares. Another example, so this is also one of the lab, was interfacing a gas sensor with Arduino. Okay, so the example was MOS gas sensor that is for alcohol detection. uh, so yeah, the video was self-explanatory, and if you are working with sensors and interfacing sensors with Arduinos, and then you must have already know like how to interface the sensor with Arduino. There are a few other videos in earlier weeks as well. Okay, so if there is any question you can ask. I'm taking a pause. Next I will go to the questions. So, I'm asking the two of you. So, are you working on designing a sensor? So in what area you are working? Like in simulation of sensor, or you are actually making sensor, or working in interfacing like a sensor with some circuit, or maybe you are taking this course just for you are working in fabrication. Okay, gas sensors. Yeah, I did worked on gas sensors in my masters. Okay, yeah, so that was my MTech thesis. I also worked in fabrication of sensor for sulfur dioxide sensing. Okay, thank you. Okay, I'll go to the questions now. Again, I will write down the question first, like all other sessions, and wait for some time so that you can tell me the answer. Which oxidation process produces a higher quality more uniform SiO2 layer? Option A is wet oxidation. Option B is dry oxidation. And C is thermal evaporation. So you can tell me the answer. And you can also think like why the certain technique gives us higher quality and good like more uniform as outer layer compared to the other techniques. The comparison between different techniques is also important. So there, as I tell you that I already mentioned you many times that often there are certain trade-offs. One thing will be good in one process, and other thing will be good in other process. Okay. Someone is on unmute. Thermal, the option is thermal evaporation. Okay. So we don't go for thermal evaporation of SiO2. Thermal, like any other process, will also involves like high temperature, so but not thermal evaporation in this case. So we normally make grow SiO2 layer. So see, there are two terms. One is growth, one is deposition. Deposition is like when we have a material, target material, and we have a substrate. So evaporation is a deposition techniques. Now wet oxidation or dry oxidation is basically growth. So we use the silicon substrate and we grow SiO2 on top of it. So certain portion of silicon is also consumed during the growth. Okay, so that is growth and that is deposition. So we mostly grow SiO2 on silicon. We can deposit SiO2 as I mentioned using sputtering or PECVD or some deposition techniques. But on SiO2 we normally go for oxidation, either dry oxidation or wet oxidation. Now among these two, which one gives us a higher quality and more uniform SiO2 layer? That is the question. Okay, so these sessions are so I'm recording the sessions and these live sessions, and also I upload it. I will, so there is an announcement section, so you can see here. So these are mainly live sessions so that you can like solve problems along with me. If you cannot attend for certain reason, then you can go here, you will find the recordings. Okay, but I encourage you to attend the session so that if you have some doubt, then you can ask in this session itself. Okay, someone give answer as wet oxidation. So actually the answer is dry oxidation. Dry oxidation gives us higher quality SiO2 layer. Okay, I will explain little bit. So what happens in SiO2 growth? I'm not talking about deposition, in growth. So what happens? You start with a silicon wafer. Okay. Now you elevate it. You do the oxidation process at a high temperature. That the oxidation process will be dependent on the temperature as well. Now what you can do is that you can do it either you can either go for wet oxidation or dry oxidation. Wet oxidation means you will use water vapor, so there is also oxidant or like oxygen that will react with silicon and will make SiO2. Dry oxidation will directly use oxygen gas. Now what happens when you do oxidation? There will be growth of SiO2 layer, and this is silicon, and there will be SiO2. Okay. Now some portion of your silicon will be consumed here. So if this thickness is say T oxide SiO2, then 46% of TOX is actually from silicon, and rest 54% will be of oxide. So your this thickness will be less. So if this is your thickness of silicon and this is your thickness of silicon initially, T naught say, then your T naught SiO2 will be more than T of SiO2. So this is the difference between growth and deposition. That's just want to discuss. Okay, deposition will be like uh, a material is deposited on silicon. Okay, there is no change on the substrate. Now dry oxidation is often used to make good quality of silicon dioxide, as I have shown you here. So the applications of SiO2 are different. Say you want to grow a gate oxide, okay, that is the part of your device, part of your MOSFET. Then you want a gate oxide that is of very high quality, and then you go for dry oxidation. Okay, the dry oxidation will give you less defect, more uniform SiO2 layer, but dry oxidation is much slower than wet oxidation. Okay, dry oxidation produces a thinner but higher quality oxide with uh, less defects. Okay, but the process is slower. So if you want to grow thick oxide like masking oxide, then we normally go for wet oxidation using water vapor. Okay, so if you are interested, like I don't want to confuse you much, so how the oxidation process happens on silicon, that is like a altogether different topic. It involves like a lot of modeling and other things. As I have shown you the book here, I have with me silicon VLSI technology. You can find the oxidation model in this book also. Now how the oxidation happens. So initially oxygen will react with silicon and it will create SiO2. So after a certain thickness of SiO2 is formed here, so this is a thin layer of SiO2. Now how oxygen will react with silicon? So oxygen has to diffuse through this layer, then react at this interface, right? So this is like a diffusion process, diffusion of water molecule or water vapor or diffusion of oxygen gas is like important, like how oxygen or water vapor will diffuse. Now then some oxygen will sit here and will react. Now it has this kind of like this two phenomena going on. One is the diffusion of this oxygen, like water vapor or oxygen gas, and then the reaction is happening. Okay, now based on that, actually these like how the oxidation process happens based on diffusion and surface reaction. What are the difference, like what are the difference in terms of this diffusion constant and the process of diffusion and the surface reaction. Those things are different for wet oxidation and dry oxidation, and that is why dry oxidation, if you look at the numbers, like how the diffusion happens and how the surface reaction happens, based on those numbers, dry oxidation is slower compared to wet oxidation. Okay, so wet oxidation is faster, but that also leads to some defects. So again, based on the application where we want to use our silicon dioxide layer, we will either choose wet oxidation or dry oxidation. Okay, this is when we want to make when we grow silicon dioxide on silicon. Now if we have a different substrate, if we just want to deposit SiO2 layer on a different substrate, say, then we will go for other technique like sputtering or PECVD. Okay, that is deposition and this is growth. Okay, I hope it is clear. I'll go to the next question. So this is the question, I already have it. I have already discussed what is the primary purpose of flats in silicon wafers. So I have shown you the figure. So these are different types of silicon substrates. So this is the primary flat and this is the secondary flat. So what are the main purpose of this flats in silicon wafer, and how we can identify, like based on the flats, like what type of wafer is this? You can frame the answer and write in the chat box. I will wait for 1 to 2 minutes. You can write what primary flats indicate, what secondary flat indicates, what the respective position of primary and secondary flats indicates. I'll give you the question here also. If only one flat means 111 p type. Yeah, that is correct. So it will help us to find the type of semiconductor. It will help us to find the doping type in our silicon wafer. That will be more appropriate. Okay, so whether it is N type or P type, and also what is the yes so what is the orientation of the wafer, whether it is a 100 or 111. Okay, so that is the main purpose of using wafers. So if you are interested so in nowadays many wafers actually there is no flat, so they use a notch on the wafer. Okay, that is to save space and all, but most of the wafer that I have seen, like those we use in our lab, is they have flats. Like I don't know, for bigger wafers, like and those are used in industries. There, instead of a flat, like a small notch will be there, that will indicate this orientation and type of the wafer. But as of now we will stick to this flats, okay, for orientation and doping information. So I'll write the answer, so I will upload this, that is why. To indicate wafer orientation, okay, 100 or 111, and doping type. the primary flat is the longer one, and it helps in identifying wafer orientation. So you know that this primary flat is along 110 direction. So based on that we can determine whether it is 100 or 111 wafer. Okay. And the secondary flat provides the doping information. Okay, let's go to the next question. So this is a true or false question. The question is SiO2 can be used as a masking layer for wet etching processes involving KOH. Whether it is true or false. It's a very simple answer. You can, I think all of you can answer me in the chat box, and also tell me the reason why you think that this is true or false. Okay, you can ask me the doubt, whatever doubt you have related to fabrication. I will try to answer if I know the answer, otherwise, I will note down the question and let you know in the next session, maybe. Okay, so by the time you write your question in the chat box, so you have also given the answer is true. Yes, we can use SiO2 layer as a masking layer in case of wet etching process that involves KOH. So KOH is used in etching of silicon, okay, as you know, and it etches away silicon but not SiO2. That is why there is the reason why you can use SiO2 as a masking layer. And it is very useful for MEMS fabrication, because as I mentioned you that QH is a wet etchant, so the etching rate will be faster. Okay. And because it can be used as a etchant for silicon, it can be easily used in bulk micro machining, which is a like often used technique for MEMS fabrication. Okay. So I'm giving you the small questions because good answer is A. Because this kind of questions are there in your assignments as well. Used as a masking layer. So this is one example. Okay. So shadow mask, see, it depends. I cannot give you like a definite answer. Uh, it depends on like where you are doing your project and what sort of facilities available nearby. Okay. So I know that this process can be done in our institute, but I am not sure if people from outside our institute can avail the facility or not. So maybe you can ask in your nearby institute if it is not available in your institute. For mask and pattern, so if you want like a shadow mask, then definitely some material that can sustain a bit of a higher temperature. See, it depends on what material that you are depositing. uh, what is your material that you want to go for deposition, because the deposition condition will determine what kind of mask you should use as a shadow mask, right? Your mask should not be damaged during the deposition technique. Okay, I think that is the only criteria. Otherwise, just you, if you are using a shadow mask, then you just want to cover your areas where you don't want deposition. Okay, if you are using a chemical method, then I'm not sure the chemical process may degrade your. See, as I don't know what is your material that you are going to deposit, so and what is the process you are uh, using, you will be using for deposition. So I cannot tell you the mask material that you are going to use as a mask. The only thing I can tell you that it should not get damaged during the process, and it should not react with your uh, layers that you are going to deposit, or like the layers underneath it. Okay, it should not it should not create any problem to your process, whatever process that you are using. Okay, any non-reactive material, any material that can sustain like high temperature, if you are going for deposition at a bit higher temperature, I think those material will work. Like you just want to cover some portion uh, just for deposition. So I discussed you that we make steps for thickness measurement. Okay, ideal case will be we will go for photoresist, uh, we will go for photolithography, we'll make those patterns using photoresist, and then we remove the photoresist layer. So that is the standard process. But sometimes what we do, we use like a tape, normal tape, not normal tape, actually we do the deposition at a very high temperature, so we want a tape that can sustain a high temperature, so we use a tape like that can sustain a high temperature, and we just make the steps. So masking your layer with a tape, that is also like a shadow masking, right? You can use a PET sheet and make your patterns. If your patterns are not that very small, okay, you can just cut out pieces where you want deposition, that also you can use as a mask, right? But again, if the dimensions are not very critical for your case and your dimensions are not very small, then only you can go for this kind of mask. Otherwise, if your dimensions are very small, then you should go for photolithography for accurate deposition or for accurate dimensions. Okay, so I'm just giving you, so it depends on what facilities are available with you. So I'm just telling you from my experience that what we have used, somehow we just mask the areas where we don't want deposition, and we do this only for like uh, some devices, some films where we don't need precision. Okay, again, if you need precision, if you need precise dimension, then you should go for like you should make your mask somewhere so that you get precise dimensions. Okay, and if your dimensions are very small, then you should go for photolithography. Okay. I think if you have further doubts, uh, then we can discuss later. You can find my email ID also. If you want to ask, then you can mail me also. But I'm just moving to the next question so that everyone can participate. Okay, so I'll write down the next question. Why is color based thickness measurement of SiO2 less accurate than ellipsometry? If we want to know the exact thickness, then we go for ellipsometry rather than color based thickness measurement. What is the reason? Colors can be affected by viewing angles. Option B is there can be like human error. Option C is color chart only provides approximate thickness. Last option is all of the above. I'll take a pause, you can write the answer in the chat box. We have already discussed this, so I am expecting the correct answer from your side. Option D. Yes. Yes, the answer is all of the above. So, color based measurement of SiO2. So, this is actually a quick and easy technique for determining the thickness of SiO2. Uh, but maybe it will not be as accurate as ellipsometry or any other thickness measurement that is done normally using an instrument. One reason is human error. Okay. uh, Colors can be affected by viewing angle as well. If you remember the equation that I mentioned you earlier, it was also discussed in the class. So this is the condition for having constructive interference. This is when the incident angle is 0 degree. Okay, the angle of incident, this theta angle, theta or phi, whatever you call. If it is not 0 degree, then there will be another term which is cos theta or cos phi, depending upon what you are like what is the variable that you are using to denote incident angle. Okay, that term will also come, and that will change your result a bit, change your calculation a bit. Okay, so that is why it is also important that what is the viewing angle, and it is not easy to like actually measure or estimate also when you are just relying on your eyes, not on some instrument. Okay. And another thing is that the color charts only provide approximate thickness. Okay. The chart that was shown in the lecture videos, I hope that you remember this, like that chart. The thickness of SiO2 was in x axis, and what is the relative and reflection or relative intensity of reflected light, that was given in the y-axis. Okay, now sometimes I know that the colors can be confusing, like so many people confuse with bluish kind of color with greenish kind of color. Okay, so it is not accurate. So again, there is a possibility of human error. Okay, that is why we go for accurate measurement we go for ellipsometry, if which is a non-destructive technique. And we can also go for surface profilometer, or if we want, if we have a step in our film And this is a destructive, not that destructive, but it's not anymore a thin film. There is a step, so that's why we call it a destructive technique. But most accurate will be ellipsometry, uh, which is a non-destructive technique. Okay, but again, people use this color-based thickness measurement because it's very accurate. Like, you don't need any uh, instrument for that, and based on the expertise, the thickness can be pretty close to the actual thickness. Okay, but for that, you have to work a lot with silicon and silicon dioxide wafers to accurately measure like the thickness, or tell the thickness just by looking at the color. And this is for SiO2. If we have other material in other some like thin film material, we don't have this kind of color based thickness measurement option, then we go for ellipsometry or surface profilometer or any other thickness measurement technique. Okay, let's go to the next question. Why is a vacuum environment required in thermal evaporation? Option A is to prevent oxidation of target material. To allow precise control of thickness. To minimize collisions between vapor atoms and other molecules present. Option D is all of the above. You can tell me the answer. option D. Yes, option D is the correct answer. But why do you think that option D is the correct answer? All of you have given the correct answer. The answer is all of the above. So, what happens? Why we need vacuum? It prevents oxidation of target material. So you know that we normally do the thermal evaporation at a very high temperature, and like most of the times oxidation processes, uh, those happens at a particular temperature, usually at a very high temperature. Okay. Say you have some metal, say aluminum, and if there is oxygen inside your chamber, uh, where you are going to do thermal evaporation, then your aluminum will become Al2O3 if the oxidation conditions are satisfied. Okay, it can happen with other material also, with copper as well. Okay, so we have done like sputtering of copper. We often face this problem of oxidation of copper target. Okay, this happens like a thin oxide layer uh, most of the time present on your target material. So to prevent that, and to prevent this kind of reaction happen at very high temperature, or any unwanted reaction that can happen at high temperature inside the chamber, uh, with the target material or with the substrate or with the film deposited uh, after evaporation. So to prevent all of those, we need a vacuum environment. And your as I mentioned you earlier also, if your vacuum is better, like if your vacuum is good, then your film quality will also be good. Okay, because your film will be very pure and it will be uniform. And another reason, mainly for thermal evaporation, we actually do the evaporation at a very good vacuum environment also. This is because you have seen the thermal evaporator system. So the evaporated material will move like this, and if there is another like gas molecule or something else, it might get scattered, and it might get deposit somewhere here, like at the chamber walls. Okay, but what you want a very good uniform deposition on your substrate. So you want all the evaporated material to move in the straight line path, like towards upward, and not sit and somewhere else. Okay, so that is why also vacuum environment is important in thermal evaporation as well as in beam evaporation. Sputtering is bit different. Okay, so about sputtering I have discussed earlier. There also we create vacuum so that there is no contamination, but during sputtering we don't maintain that high vacuum. Okay, so this vacuum requirement is process dependent, and for thermal evaporation we want a very good vacuum so that our evaporated material directly evaporate from the target and sits at the substrate, not somewhere else. Okay, so I'll write few points here. reduces scattering, and because of these two, we get improved film quality and good thickness, like uniform thickness. Okay, let's go to the next question. Okay, so there were few lab classes or tutorial classes on console. So I have included a few like a small questions on console multiphysics. I am not sure how many of you are using or have used console, but based on the videos those were given for this week, you will be able to answer this question. Console allows simulations involving multiple physics at the same time. So whether this statement is true or false. You can tell me the answer, and also you can let me know if you have used console or any similar software for your work. Okay, it's true. And okay, you will be using next month. Okay, so I hope that so that means maybe you have the access of console. So yeah, it's a good tool. Many people use it, and lot of resources are available. Like you can get YouTube videos. Console often organize webinars. You can attend those also if you need. So I have attended few earlier, and those webinars are available in their websites, I guess, if I remember correctly. So you will be able to get help, and uh, because it's a very well known and well used software, so many people use it. So it's actually easy. I won't say easy, but it's a good tool, because many times getting help from fellow user is possible. Okay, so the answer is true. Okay, console, the name of the software itself is console multiphysics. Okay, so different physics are available, like you can work on different things. I can give you few physics those are available, like electromagnetics, like wave optics you can do. Okay, fluid flow for fluid flow analysis also there will be some physics available, and then heat transfer module is also available. Chemical reaction, these are useful for like sensor design. Mass transport. Okay, so these are useful for different types of sensor design. Okay, if you have the access you can look and try few sensor design by yourself. Many examples are already given, like there are examples available in the application library. You can just go through those also for better understanding. Okay, so let me see if I have time. Okay, we have some more time, so I will give you this question. I already have it. So another video was on uh, lab class was on interfacing gas sensor with Arduino. Okay, so we have already discussed how we can interface a sensor with Arduino. So this question is on the sensor that was used in the class was MQ3 gas sensor, and the sensor is used to detect particular gas. Okay, what kind of analyte or gas it detects, that is the question, whether it is carbon dioxide, alcohol, hydrogen or ammonia. So you can tell me the answer in the chat box. Also you can mention few other details about this MQ3 gas sensor, like what is the working mechanism there, what kind of sensing material is used in this sensor. Okay, if you remember, if you have watched the videos, you must have remember all these details. Okay, you can tell me in the chat box also, you can recall and let me know. It's B, it's a ethanol gas sensor, and tin oxide is used here. Principle is redox reaction and output will be resistance change. Okay, so that's a good answer. So the sensing material is tin oxide, so it is a MOS gas sensor, metal oxide semiconductor gas sensor. So what can be other MOS sensor? It can be based on ZNO. Okay, there are other few materials as well, and the principle is redox reaction, that is the oxidation reduction reaction, that is the working mechanism, and the output is resistant change. Yes, so what type of output it has? MQ3 sensor, it has two types of output, right? If you remember from the class, so it has two types of output. The main output is analog in nature. Okay, it gives an analog output, change in resistance, as well as one digital output also, if we can use it as a comparator. If you remember, like a potentiometer was connected, and if the gas concentration is say higher than certain level, we can like make a comparison with the sensor output and the concentration of gas, and based on that we can set a limiter value. Say that if concentration is higher than this, then this digital output pin will be high or low. so I don't remember the exact connection, but it has like this two kind of output. One is analog, which is the main output, and we can use it as a digital output uh, signal also, so to give some indication as that the alcohol level is too high. Okay, that can be used for some safety monitoring system, say uh, drink and drive cases for those. Okay, so it is a tin oxide based sensor, SNO2. So this is the sensing material. Then working mechanism is redox reaction. So based on this reaction, the resistance of the material, sensing material, will change, and that change can be detected. Okay. Output, it provides an analog output and a digital output as well. So if you remember, it's a four terminal sensor, four terminal device. So two pins are to provide the power, and then to get the output we have basically two output. Now many of this SNO2 based sensors, so these operate at higher temperature, so this kind of sensor also includes a heater. So that is why the heater design along with sensor is very important. This was discussed multiple times in the lecture videos as well, how we can integrate a sensor within a heater, like a heater design below, an oxide layer in between, and on top of that interdigitated electrode along with the sensing material for detection of some analytes, say for gas sensing. Okay, so that's all for this session. If you have any doubt, you can ask, or I will end the session because it's almost 8. Okay, I'm waiting for like for a minute or so. So if there is, okay, you can find my mail ID in the beginning of. So if you have some really like doubt, then you can mail me, like, but don't expect that I will be able to answer or send you and reply immediately. So you will find it here. Okay, you can check the lecture material. Okay, you will find it here. I upload these uh, PPTs periodically, like after every session. You will find any of those. Okay. Okay, if there is no question, let's end the session here. Thank you for attending the session, and I hope that the session was useful, and see you in the next session on next Tuesday. Okay.